Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on trigonometry degree level chapter complex arguments lecture number 1, in which I will derive logarithms of complex quantities. Firstly, we find the exponential values of sine and cosine functions. Since we know that e to the power x equal to 1 plus x square by factorial 2 plus x cube by factorial 3 plus x to the power 4 by factorial 4 plus x to the power 5 by factorial 5 plus dot 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 dot. This is number 1. Replacing x by I theta, we get e to the power I theta equal to 1 plus, in place of x, I theta, plus in place of x, I theta square by factorial 2 plus I theta to the power 3 by factorial 3 plus I theta to the power 4 by factorial 4 plus I theta to the power 5 by factorial 5 plus dot dot dot, and this is equal to 1 plus I theta plus I square means minus, so here we write minus theta square by factorial 2, I cube is minus I theta cube by factorial 3, I to the power 4 is 1, so this is theta to the power 4 by factorial 4, I to the power 5 is I plus I theta to the power 5 by factorial 5 plus dot 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 dot. Now we take these quantities, means free from I. We take the quantities free from I. 1 minus theta square by factorial 2 plus theta to the power 4 by factorial 4 minus dot 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 dot. Then we take quantities with I. We take common I. Remains theta minus theta cube by factorial 3 plus theta to the power 5 by factorial 5 minus dot 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 dot. This bracket represents cos theta and this bracket represents sin theta. So we get the formula e to the power I theta equal to cos theta plus I sin theta. This is number 2. Replacing theta by minus theta in 2, we get e to the power minus I theta equal to cos minus theta plus I sin minus theta. Cos minus theta is cos theta and sin minus theta is minus sin theta. So here minus I sin theta implies that e to the power minus I theta equal to cos theta minus I sin theta. This is number 3. Adding 2 and 3, we get e to the power I theta plus e to the power minus I theta equal to, here minus I sin theta, here plus I sin theta, cancel. So remains 2 cos theta. Implies that cos theta equal to e to the power I theta plus e to the power minus I theta by 2. This is another formula for finding cos theta as exponential values. This is the exponential value of the cos theta. Subtracting 3 from 2, we get e to the power I theta minus e to the power minus I theta. This is equal to, here cos theta cancel, remains 2I sin theta. Implies that sin theta equal to e to the power I theta minus e to the power minus I theta by 2I. This is the exponential value of sin theta. This is number 4 and this is number 5. In 4 and 5, we get the exponential values of cosine and sine functions. Equations 4 and 5 are called Euler's exponential values. Now we solve a question. Question is, with the help of exponential values of sine and cosine functions, prove that number 1, cos theta plus phi equal to cos theta cos phi minus sin theta sin phi. Number 2, sin theta plus phi equal to sin theta multiply cos phi plus cos theta multiply sin phi. Now we solve this. Since e to the power I theta equal to cos theta plus I sin theta, therefore e to the power I theta plus phi equal to cos theta plus phi plus I sin theta plus phi. We may write this left side as e to the power I theta plus I phi. This equal to cos theta plus phi plus I sin theta plus phi. Left side is e to the power I theta multiply e to the power I phi, cos theta plus phi plus I sin theta plus phi. Implies that e to the power I theta is cos theta plus I sin theta. E to the power I phi is cos phi plus I sin phi, and right side is same, cos theta plus phi plus I sin theta plus phi implies that we multiply and get cos theta cos phi minus sin theta sin phi plus I sin theta cos phi plus cos theta sin phi. This equal to right side cos theta plus phi plus I sin theta plus phi. Let this is number 1. Equating real and imaginary parts of both sides. We get cos theta plus phi, this is real part and this is real part in left side, this is real part in right side. So this will be cos theta cos phi minus sin theta sin phi, and imaginary part of right side is sin theta plus phi. Here this is the imaginary part of left side, this is sin theta cos phi plus cos theta sin phi, and proved. Now I will show the periodicity nature of complex quantities. Before showing this, I would like to give you the concept of the periodic function. Let fx be a function of x if fx plus t equal to fx for least value of t, then t is called period of this function, because after adding t we get same value of the function fx. For example, let we have fx equal to cos x. Now fx plus 2 pi equal to cos x plus 2 pi. This equal to cos x. So here period is 2 pi, because adding 2 pi with x we get same value of the function cos x. Also fx plus 2n pi equal to cos x plus 2n pi, n equal to 0, 1, 2, dot 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 dot, and this equal to cos x plus 2n pi is cos x, which is fx. Here also cos x is fx. Here we have added 2n pi with x and we get the same value of the function fx. But we may not say that 2n pi be the period of the function, because the least value 2 pi for n equal to 1 here, 2n pi, n equal to 1, then this is 2 pi. We have added here least value with x and we obtain the original value of the function. So 2 pi is the period of this function. Now we give the concept of periodicity of the complex quantity. Let z is a complex number such that z equal to x plus iy. X and y are real numbers. Let this is number 1. Let E be a function Ez equal to e to the power z, and this will be e to the power x plus iy. This will be e to the power x multiply e to the power iy, and this will be equal to e to the power x multiply, this is cos y plus I sin y, because e to the power I theta equal to cos theta plus I sin theta. We may write this e to the power x multiply cos y plus 2n pi. Cos y plus 2n pi is cos y. Similarly, I sin y plus 2n pi, and this will be equal to e to the power x multiply. We may write this as e to the power I y plus 2n pi, and we may write this e to the power x plus iy plus I 2n pi, and we may write this e to the power x plus iy is z, z plus 2n pi I. Here e to the power z is ez, then this will be written as e z plus 2n pi I. Here we write Ez. Here Ez equal to Ez plus 2n pi. Since from 2 we get Ez plus 2n pi I equal to Ez n equal to 0, 1, 2, dot 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 dot. Here if we put the value n equal to 0, then we get Ez equal to Ez. But if we put n equal to 1, we get Ez plus 2 pi I. Value of n is 1 equal to Ez. So we have added 2 pi I minimum value with z. Then we get the original value of the function. Therefore 2 pi I is the period of this function. This complex function. Now we find the logarithm of complex quantities. Let z equal to x plus iy, x and y are real numbers. Let e to the power z equal to w and w equal to u plus iv. This is number 1. This is number 2. From here we get log base e w equal to z. So logarithm of w is z. This is number 3. Since w equal to e to the power z, we may write this e to the power z multiply 1. This is equal to e to the power z multiply e to the power 2n pi I. In place of 1 we have written this because e to the power 2n pi I equal to cos 2n pi plus I sin 2n pi. Cos 2n pi is 1 plus I sin 2n pi is 0 and this is 1. We may write this e to the power z plus 2n pi I. Here in 2 we see that e to the power z equal to w. Here we see that e to the power z plus 2n pi I equal to w. And from this we have used the concept of logarithm. Log base e w equal to z. Here we write logarithm, but the value of the index is here different. So we use LOG, capital LOG, logarithm. Base e w equal to z plus 2n pi I, and from 3 z equal to log EW, and we write capital LOG E base E W equal to small log log base E W plus 2n pi I. This is the relation between small log logarithm and capital Log logarithm of complex quantities. This is number 4. This is number 5. Since in 4 value of n be integers, therefore logarithm log is many valued function because here if we change the value of n we get different values here. So this function gives many values. The principal value, this is the principal value of this logarithm. The principal value of this logarithm is small log w logarithm. Now we evaluate log alpha plus I beta. Here log capital L capital L O G, alpha plus I beta, where alpha and beta are real numbers. Let alpha equal to r cos theta and beta equal to r sin theta, implies that alpha square plus beta square equal to r square cos square theta plus r square sin square theta. This is equal to r square common cos square theta plus sin square theta. This is equal to r square multiply 1. This is equal to r square. Let this is number 1, this is number 2, this is number 3. Beta by alpha equal to r sin theta by r cos theta. This is equal to tan theta, implies that theta equal to tan inverse beta by alpha. This is number 4. Using logarithm in both sides of 3, we get log alpha square plus beta square equal to log r square. This is equal to 2 log r, implies that log r equal to half log alpha square plus beta square. This is number 5. Now alpha plus I beta equal to alpha equal to r cos theta plus I beta equal to r sin theta. This is equal to r common cos theta plus I sin theta. This is equal to r e to the power I theta. This is equal to r e to the power I theta multiply e to the power 2n pi I, n equal to 0, 1, 2, dot 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 dot. Since e to the power 2n pi I equal to 1, because this is cos 2n pi plus I sin 2n pi. Cos 2n pi is 1 and sin 2n pi is 0. This is equal to r e to the power I theta plus 2n pi, implies that capital Log log alpha plus I beta. This is equal to capital L Og r e to the power I theta plus 2n pi. This is capital Log log r plus Log e to the power I theta plus 2n pi. Since r is real number, so here we write log r, small log r and capital log r, same, plus here I theta plus 2n pi. This log r is half log alpha square plus beta square plus I, here 2n pi plus theta equal to tan inverse beta by alpha. This is the required result. Since we know that capital L log W equal to small l log W plus 2 n pi I, when n equal to 0, then capital L log W equal to small l log W. Using this concept, here n equal to 0, we get here capital L log becomes small l log alpha plus I beta equal to half log alpha square plus beta square plus I tan inverse beta by alpha. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.